Similar to exponential growth, we also have exponential decay models where the decay rate is proportional to the current size. And the exponential decay, the model is actually the same thing as exponential growth, but our exponent is a negative exponent. Okay, a times e to the negative bx, where b is positive. So if b is positive, then negative b is negative. So the form of exponential decay is actually the exact same. In fact, if you want, and actually this is usually what I do, you can just write a times e to the bx, but then know that b is going to end up as a negative number. Okay, so either one of these forms is fine. It doesn't really matter how you set it up, because however you set it up, the b will come out properly using the data that you have. The most common example of exponential decay is with half-life of radioactive substances. So a radioactive substance is an element that loses mass over time, and it follows an exponential decay model, the amount of mass. And we often describe this decay rate as a half-life, which is the amount of time that it takes for an initial quantity to lose half of its mass. So one of the most commonly used applications of this is the half-life of carbon-14. It's used for carbon dating. And carbon-14 has a half-life of 5,715 years. So if we take a sample of carbon-14 that initially has 28 grams, we want to find the amount left after 1,000 years. So first what we're going to do is we're going to write our exponential model, and we're going to figure out what that b is. I'm going to write it like this: y equals a times e to the bx. Again, if I write it like this, b is going to end up being negative because it's decay. And I'm going to use the fact that I know, well, I'm starting off with 28 grams. That's a. All right, a is our initial value. And so I can put that in. Okay, so that's nice. So really the only thing now I need is b. Well, I also happen to know that after 5,715 years, so if I put that in for x, I should lose half of my mass. So I should end up with 14 grams. So 14 equals 28, e to the 5,715 times b. All right, x is that half-life. And now I can go ahead and solve for b. Let's go ahead and divide both sides by 28. That gives me 1/2 equals e to the 5,715b, and take the natural log. The natural log of 1/2 is equal to 5,715b, and then divide by 5,715. So the natural log of 1/2 over 5,715, that is b. We can plug that into our calculator, and we should get a negative number. Let's just double check, huh? Natural log of 1/2 over 5,715. Okay, I'm going to go ahead and hit Control-Enter, and there we go. We have a negative number. That's our b. Now I'm going to take that number and I'm going to store it in the variable b. I'm going to hit Control and the STO arrow. That's going to store it in the variable b and hit Enter. Now every time I type b, my calculator knows that it's this number. Okay. All right, now I've got my model. I know y equals, okay, a, which was 28, and then e to that b number, natural log of 1/2 over 5,715 times x. There's my model. And I'd like to know how much I've got after 1,000 years. And so we're going to go and just plug 1,000 into this. All right, so we've got 28, e to the, and then that number right there is b, so b, which I already stored in the variable b, so I've got that, times the 1,000 years. And I go ahead and hit Enter. It gives me an exact number. Let's go ahead and hit Control-Enter, and that'll give us a better idea. So after 1,000 years, that 28 grams has reduced now down to about 24.8 grams.